Good morning, everyone. Today we're going to look at how do we find the volume of a pyramid or a cone, and then we'll use those formulas to help us solve problems. So what I'd like to do to start is if you could go over to the table and grab your three pyramids from yesterday and reassemble them, if they're not already, into the triangular prism that we ended up with from lesson 12. So if the sub would press pause right now on the video, that would be wonderful. Give the kids a chance to grab their supplies and work through this and create their solid. Okay, great. Now that you had a chance to grab your supplies, what we're going to do is we're going to actually analyze how that was created. So all you need is your 3D pyramids. Suppose that we split the prism that you have into the three solids. And how did they do that? Well, you already have it here, but if I was to take the first pyramid by splitting off or slicing through the points E, D, and C. So imagine a plane, three-dimensional plane, slicing that off, that would give you this first triangular pyramid, P1. And then if we did the same thing and sliced the other pieces that were left over, we'd end up with the shape P2 and P3. And just for example, P1, you can see that the yellow side or face would be shared with the yellow side or face of P2. And then we could highlight other pieces as well. Our job then is to use these three individual pieces and the bases or faces that they have in common to help us come up with the formula for the volume of a single pyramid. Now, you might already have something in mind. So let's start off on page 298. If you would turn to page 298, what I would like you to do is using P1 and P3. You can position the shapes kind of like I have here. That way you can see where they came from based off of the original prism. But answer number 1, part A, B, and C, and we'll go over those together here shortly. So if the sub would press pause right now in the video, let's give the kids maybe 3-4 minutes to work through parts A, B, and C on number 1. All right, great. So part A, think of the faces marked P1 and P3 as the bases of the pyramids. These triangles are the two bases of the original prism. So I highlighted those two pieces. So if I highlighted the base of each of the original prism, remember a prism, we're actually going to use the definition of a prism to help us out here. But a prism has to have two congruent bases. So how do the areas of these two bases compare? Well, because this is centered right at the origin, and we know that an axis is a 90-degree angle, these are actually two right triangles. And you could calculate the area if you wanted to, and you would do 2 times 3 times a half. So 2 times 3 is 6, cut in half would be 3. I would get 3 units squared for the area of each one of these triangles. But you don't really need that if you knew that these two bases came from a prism. So how do we know the area of the two bases compare? Well, in a prism, the base areas have to be the same because the definition of a prism is it has two congruent bases. So we already know that the areas are the same based off of the fact it formed a prism, or we could calculate that. How do we know the heights of P1 and P3 compare? Well, you could kind of use the scale on the side here. If point D is the highest point, if that's the apex of P3, the highest value it's going to reach is 4. And then likewise, if we're already at the height of 4 on the base, then its apex would be down here at 0, so that height would be 4 as well. The other way to think of it is because the two solids were a prism in the beginning, the distance between the two bases have to be equal. So regardless of how you think of it, you know the height of both of these pyramids are the same. So if the bases have the same area and the pyramids have the same height, then we actually had something called Cavallari's principle that said if the cross-sectional area at every height is the same for both solids, they have the same base, same height, same area of the base, same height, then the volumes have to be the same, right? Another way to think of this is if I completely rotated the first P1 triangular pyramid, it would rotate down and match up with the original, and they'd have the same base, same height, they'd be two congruent figures. So therefore the volumes would have to be the same. So what I'd like you to do now is turn to page 299, and this time we're going to compare P2 and P3. I highlighted the two areas that they want you to compare. They call them the gray shaded triangles. I'd like you to answer parts A and B, and if the sub could then press pause, we'll go over the answers in about 3 or 4 minutes. So let's take a look at part A. What if we know that if we had our original prism, so the original solid made up of all three pyramids, if we looked at that, the two blue shaded faces are actually one of the faces of the prism, one of the rectangular faces. Well, what we did was we divided that right down the middle. So I took a rectangle that has the same length and the same width, or same base and height, and I divided that right down the middle. Well, if that's the case, then those two areas have to be congruent. So here, you think of these as the bases of my new pyramid, triangular pyramid. I have two congruent bases. Part B said the heights of the pyramids, P2 and P3, are equal because when the assembled prism, the height along the lines coincide with the length of the prism. So they're referring to this distance right here. And if the shape in P2 that I'm looking at is the triangular pyramid with this as the base, then the apex is point C. So the height would have to be the same. And notice if I called the base on P3 this blue highlighted area, then its height is also the length for C, because this is formed at a perpendicular 90-degree angle. So if the area of the bases are the same and they have the exact same height, then we know that the volumes must be equal. So our logic, same area of the base, same height, equal volumes. Now, what I'd like you to do is finish on page 299. Go ahead and write a conclusion for number 3 and 4. And if the sub could pause the video, we'll go over it in about 2 minutes. So let's take a look at what we know. You didn't have to have this written down exactly like I have. I'm just kind of showing you my thinking here. So what did we learn? We discovered that the volume of the pyramid 1 was equal to the volume of the pyramid 2. The volume of pyramid 2 was equal to the volume of pyramid 3. Well, if 1 is equal to 2 and 2 is equal to 3, then we know by the transitive property that the volume of the pyramid 1 is equal to the volume of the pyramid 3, which basically is a fancy way of saying all three pyramids have the same volume. Right, so now, how does the volume of each pyramid compare to the volume of the prism itself? Well, the volume of the prism is 3 times the volume of one of those pyramids. So how could we use this information to find the volume of one of the pyramids? Well, what if we just work backwards? So what if I knew the volume of a prism, which we know, we could have calculated that from day 1. What if I actually want to solve for the volume of the pyramid? Well, if I move this 3 over to the other side, then we're going to come up with the volume formula of a pyramid is equal to 1/3 the volume of a prism. But let's take that one more step further. We know that the volume of the prism is always the area of the base times the height. So here's my new formula for the volume of a pyramid. It's just 1/3 the area of the base times the height. All right, this is just a little extension. Do any of these arguments depend on the specific triangular prism that we used? So I know we just had one model in our hand, but could this work for any triangular prism? Well, this pyramid doesn't look like the ones we used in the lesson. Is it possible to create 3 pyramids with the same volume as this one and assemble that into a prism? What I'm going to do is show you this little applet here. If I can make it work. Just to show you that as long as you keep the heights the same, here we go. Watch what happens when I drag this slider to the left and the right. So here I have 3 pyramids. They have the same base, same height. Watch what happens if I drag them. Now notice, I can change their heights or their position of their apex so the height doesn't change, but their position changes. And then I rotate them around and they create another prism. So same kind of logic here is if you have any triangular prism, if you have 3 of them, they have the same base and the same height, you could potentially move or adjust the apex, keeping the height and the area of the base the same, and that would allow you to then construct a prism from that. All right, please turn to page 300 and work through problems 1, 2, 3, and 4 using our idea that we just talked about. And the sub will press pause and give you guys about 5 minutes to work on this. So let's take a look here. Each solid in the image has a height of 6 units. So they don't show it here, but we know that every single one of these solids has the same height of 6 units. The area of each solid's base is 10 units squared. The cross sections have been created in each by dilating the base using the apex as the center, with the scale factor of k being 0.5. So notice that's halfway up. Each cross section is exactly half the height, which we could determine that as half of 6 is 3, so I know that that's 3 units up. Calculate the area of each of the 3 cross sections. Well, that's where we have a little bit of a challenging problem. We don't know the measurements at those pieces, and we don't know the measurements because all we know is the area of the base. So what we have to do is we have to use the idea that we have the scale factor and we're comparing area. So going back to what we've learned in previous units, we know that the area of the base times the scale factor squared will give us the new area of the dilated cross section. So I'm going to take the fact that I know the base area is 10. Right? They gave us that. That was 10. We know our scale factor is 0.5, and that will give me the new area. So when I square 0.5, I get 0.25. When I multiply 10 by 0.25, we get 2.5 units squared. So the new area of each one of these cross sections here, maybe I could call that B prime. We could call that B prime. Area of the base translated or dilated 2.5 square units. Right? And it would be the same for each one of these. They would both be 2.5 square units. Right. Now, suppose a new cross section was created in each solid at all the same heights using some scale factor k. how would the area of the three cross sections compare? So now instead of being exactly at 0.5, what if we left it as just k? K is my scale factor. So the area of the three cross sections would all be equal because it doesn't really matter how far up you go in terms of your new height. I could go way up here, I could go just barely above the original base. Each area would be 10 times the scale factor squared because 10 is the area of the base, k is the scale factor squared, and that will always give us the new area. All right, number 3. What does this information about cross sections tell you about the volume of the three solids? Well, this is hinting at Cavallari's principle that we learned the other day. Since the cross sections at each height are equal, they have the same area, then the volume would be the same as well. So we know that these three shapes, all three of them will have the same volume because they have the same base area, the same height, and their cross-sectional areas are the same at every level. So knowing that, can we calculate the volume of each solid? Well, the nice thing about that is if they're all going to have the same solids, or same volume, then we just have to calculate one of them. Now notice that these are either a pyramid or a cone, and we just generated the formula for the volume of a pyramid. The volume of any pyramid is 1/3 the area of the base times the height. And since the area of the base and the height are the same, if I do 1/3 the area of the base is 10 times the height of 6, I will get a volume of 20 units cubed. So if you take out your blue reference sheet, we're going to annotate this theorem. We're actually going to add a little bit more to it. But it says a pyramid or a cone whose base has area b square units and whose height is in h units has a volume of 1/3 the cubic units regardless of the shape of the base or whether the solid is oblique or right. I might add one extra piece to this. Volume of any pyramid or cone, anything that comes to a point with an apex, is 1/3 the area of the base times the height. And that's our volume formula for a pyramid or a cone. All right, if you want to press pause until the students feel like they've got this down, you can hit play when they're ready. All right, so the next thing we're going to do is we're going to jump to page 306, 14.2. What I would like you to do is take this idea that we just determined the volume formula for anything that has an apex. Take the area of the base times the height and cut it into 1/3 or divide it by 3. So what I'd like you to do is each person in your group should find the volume of one of the solids, compare your work with your group when you're done, what was similar, what was different. So go ahead and divide this up, A, B, C, and D, and we'll give you about 3 minutes on this to complete your work and then compare your answers. So we'll hit pause for now. All right, let's take a look at the answers here. So volume of any pyramid is 1/3 the area of the base times the height. The area of the base is a 2x2 square, so 2 times 2 is 4. The height is 6. 1/3 of 24 is 8 feet cubed. If you had part B, this one is a little interesting because we could have used an exact answer. We'll show you that here. But for a cone, it's 1/3 the area of the base times the height. A cone has the base of a circle, so pi r squared. The radius is 2. So I did 2 squared times pi, which gave me 4 pi. And then I did 4 times 4.2 and divided that by 3, and I got 5.6 pi. This is what we call the exact answer, meaning we didn't have to round and we leave pi in the answer. If you use the pi button in your calculations, you should have got 17.593. I always round to 3 decimals when I can. That's a little more accurate than rounding to just 2 decimals or 1. All right, if you had part C. So part C here, we have a 3 by 4 right triangle on the bottom. So the area of its base is 3 times 4 times a half. So 1/3 area base times the height. I get 12 cut in half, gives me the area of the base is 6. The height of the pyramid is 7. 1/3 of 42 is 14. And then part D. This one looks like it might be the scariest, but it actually is probably the friendliest. They tell me the height and they tell me the base of the area is 32. So I don't have to do the calculations. It's just 1/3 32 times 12, which gives me 128 centimeters cubed. Double check your units. Did you put for volume? It should always be units cubed for every one of these. If you need to go back and look at these, the answers, the worked out, printed out version of the notes will be on Schoology. You can go back and check those out later on. All right, I'd like you to try page 306. We're going to start with 4.2, number 2. A particular cone has a radius of r and a height of h. I'd like you to answer parts A through C right now. We'll press pause on the video and then reveal the answers. Okay, so let's start off. One of the things I would do, and just because I'm a visual learner, is I would draw a picture of this situation. We have a cone. We know that the radius length is r and the height is h. And that kind of clues me into, we have an apex. I want to find the volume of something with an apex. So I'm going to do 1/3 the area of the base times the height. And part A, we want to write an expression for that. Well, the only thing we can actually change is the area of the base. For any cone, the area of the base is always a circle. And the area of the base for any circle is pi r squared. So a cone, the volume formula for any cone is 1/3 the area of the base, pi r squared, times the height. I don't like to memorize this because I just know 1/3 area of the base times the height. And then I always know that a cone has pi r squared as its base. So I kind of fill that in every time. I think of it as one less formula to memorize. Well, let's use that formula now and work backwards. What is the height of a cone whose volume is 16 pi units cubed and whose radius is 3? So we're going to take the fact that we want to find h. We've got to find the height. I know the volume, 16 pi. I know the radius. The only thing I don't know is h, so when you plug everything in, it now becomes an algebra problem. Your job is to work backwards to solve h. What I like to do is I like to just simplify first. So 3 squared is 9. The area of the base is 9 pi. Now notice, I've got 1/3 times 9. Well, 1/3 of 9 is just 3. So I think of this as 16 pi equals 3 pi times h. And then my goal is to get h by itself. So I need to take the 3 times pi and divide it over to the other side. And when I do that, notice how we get a pi on top and on bottom. The pi's reduce out. The 3's are gone on this side, so leaving me with just h. And then I can't reduce 16/3, so I'm just going to leave it as the height is 16/3 units. Notice how it's just units. If this was feet, it would be 16/3 feet because height is a singular length. All right, part C. What is the radius? Well, we're basically going to do the same thing. We're going to take our volume formula, but this time we know the volume is 16 pi, and we know the height is 3. So we have to work backwards to find the radius. So plug in everything that you know. And then I'm going to actually try to simplify here, but notice 1/3 times 3. That's actually really friendly because 1/3 of 3 is 1, or you can kind of think of the 3 and the 1/3 as reducing each other out. So I'm left with pi times r squared equals 16 pi. So I need to take this pi and divide it by both sides. That'll get rid of a pi on both sides. And it'll leave me with 16 equals the radius squared. And then we'll go ahead and take the square root of both sides. Square root of 16 is 4 units long. So these two problems that we just did are called problems which you work backwards on. You know the volume, you have to work backwards to find the radius or the height. All right, I think we're going to actually skip this one. I would highly recommend you go ahead and try 14.3 on page 307. I'll write my answers and put that in the notes, but we're going to skip that and have you guys jump right to the ending piece. So our big piece today is we know the volume for any pyramid or any cone is 1/3 the area of the base times the height. Your job tonight is to work on lessons 13 and 14 summaries, and then do the practice problems, checking your solutions online. Don't forget about the Delta Math. It's officially due tomorrow. Oh, no, Friday. Today's Friday for you guys. So make sure your Delta Math gets done by Friday night. Have a great day. Adios. I'll see you next week.